Good morning, everyone. My name is Simon Schabel. I'm Grid Solution Architect responsible for Central Europe, based out of Germany. My topic today is to talk about NVENC a bit more in detail. As Luke asked, it seems that this is a topic that is not well known from everyone. But before we start, I want to have a short intro of NVIDIA. Most of you maybe know NVIDIA as a gaming company, and we heard a lot about the enterprise computing part, but NVIDIA is more. There are new areas that are very fast growing, especially the automotive part, with all the autonomous driving, the new digital displays, and for sure the high-performance computing part. Yeah, let's have a look. Something changes in the last years, and NVIDIA tries to help driving these changes with delivering the right products and solutions the market demands. I made a screenshot from a very old game. Who know?
Doom.
Okay, and the year the game was released for a pint?
You're paying for the pint.
Doom.
1998, I thought.
Was Doom 1994?
The year before.
394.
93.
I remember when I saw it first time.
First time.
That was
Yeah. Well done. You get a pint later on.
Look at the resolution.
Yes, the interesting thing, game was released in '93, very high resolution. What's the reason why I showed this? I said things are changing. Have a look now, around 20 years later, we have this new Doom released 2 weeks ago or 3 weeks ago, with all this funny stuff, dynamic lighting, particle effects, multi-monitor support, and for sure 4K support. So there is a lot of change. I found more. Maybe most of you have seen in the past the next generation transcripts. This was an episode where Riker asked Data about his specifications. And Data answered his storage capacity. It's even today very huge because it's 100,000 terabytes of storage. But the interesting thing is his compute power in these days, it's 60 teraflops. Do you remember when this episode was coming out for the next pint?
I will listen. Okay, they start like 88, 89.
89.
Yeah.
Very good. So,
Who got wasted?
these 60 teraflops in these days has been 35,000 times faster than the fastest supercomputer in '89. So a very huge number. But they didn't believe that around 20 years later we just announced this new little supercomputer for deep learning, which has 170 teraflops. It's called HX1. So now it's enough with advertising, and I will start with our topic for today, NVENC, which is NVIDIA hardware encoder. And what's behind NVENC? What's it? It's a dedicated H.264 hardware chip on our graphics card. So it leaves the CPU and the GPU rendering engine to perform all the other tasks. And we introduced the NVENC chips with our capital platform. So it's already on K1 and K2, but we highly improved it on Maxwell Generation 1 and Generation 2. The performance these chips can have, can you see here in our H264 line. And there you see the big difference, for example, between K2 and M60. With K2 we have 6 possible streams with 30 frames. Compared to the M60, we have 36 possible sessions with 30 frames. So there is a huge difference in the chip itself. How does it work? Basically, today, the grid card is only used for the rendering stuff. The capture and encode part needs to be done in CPU, and this causes additional CPU load and additional latency. So, why not doing this directly on the graphics card if it's already there? So what do we do with NVENC? We now do the whole stuff here, rendering, capture and encode directly on the grid card. If we have a more detailed look of the process here, we render, we capture, put it over, and here's the NVENC engine for the hardware encoding of the stream. And the interesting thing is the latency. With NVENC, we encode in the hardware chip, so the latency is very low. In general, it's around 4 milliseconds. Compared to what you have with CPU, it's much higher and highly dependent on the CPU load the host has in general. But I want to show some slides later on that compares especially the latency. The latency itself is quite hard to measure in a VDI or thermal solver environment. So, our testing lab, Nuke's team, they did all this fancy stuff.
Fancy in the form that's really high-end tape holding that stuff to the monitor.
Yes, what they did to test the latency is the such-called click-to-photon method. They put the scope on the mouse so that you click on the mouse.
But is this just a wire into the mouse, one instead of looking at the finger? You can just wire into the mouse and collect the clicks.
Do what, sorry?
Why would you need the camera, right? You have an electronic device. It's not an analog device anyway, right?
No, there's no camera. There's a photodiode taped to the display,
Yeah,
so that when you click
you
the...
get it directly from the mouse. You don't need the camera, right? Why would you do that?
There's no... So the point is, when I click the mouse and it changes the cell or screen or whatever it is we've changed, the photodiode records the change, so it's clicked to photons. So what's the time difference between when I click to when, in this case, we went from a full screen white to a full screen black slide in PowerPoint?
Yeah, sure.
And so it would record that change, and I need to know what the milliseconds latency is between when I click the mouse and when the screen actually changes.
Sure, but you can collect signal from the mouse directly. You don't even need one camera for the screen, sure, but for the mouse.
There's no camera.
There's no camera for the mouse. It's only connected to the scope.
Yeah. There's,
Well,
Camera-
this
camera
goes to the
here
scope.
too.
What I'm saying is that fine, the scope can collect it from the mouse itself. You don't need to.
right, sure. All this is a wire
Yeah,
attachment.
yeah, I understand what you're saying.
Okay,
It's not the
there's
scope.
no mouse. There's no camera on the mouse.
One important thing to know is they did the same on a physical client to have kind of baseline, and the click to photon on a physical client has a latency of 65 milliseconds. So this is our baseline.
It's not actually true. No LAN. There's no network connectivity. It's local client,
Yeah.
local click. That's important because 65 milliseconds to click your keyboard on your laptop and have your laptop change that PowerPoint was still. People always come back to us and like, I don't know, I'm getting 150 milliseconds ping times, and I'm like, okay, that's fine, but you still have another 65 to 100 milliseconds in your transaction time on top of that. That's the problem. It's not the 150 milliseconds over the wire. It's what's the time before and after, which is why encode makes such a huge difference. Because if I can knock 50 milliseconds off of the part that doesn't involve the wire, how much further out can your user be and still get the same experience? Sorry.
Wrong.
Hey, you brought our lab up.
Yes. Unfortunately, I couldn't have the same demo that they did on GTC, but there is the link for the video. So if you are interested how this whole click to photon method is working, it's a very nice video that shows all the stuff and gives you more details. Yeah, here is once again how it would look like. Make it fast. Okay, and that's the result. And it's really interesting to see. Unfortunately, I've not mentioned it yet, but Citrix is currently supporting NVENC only on Linux, not on Windows. Therefore, the whole measurement, it's almost finished from our side, but we are not allowed to publish any slides with the Citrix measurements yet until it's officially released. Therefore, I had to put in the slides from VMware. VMware Horizon 7 already supports NVENC with Plastic Stream protocol, but Plastic Stream now already uses H.264, so the results are quite comparable. I guess it's very hard to see there behind, but I will try to explain. We have our baseline here. This is a host in idle mode, and we see here Plastic Stream encoded in CPU. We have 150 milliseconds. The same with NVENC enabled, so encoding in hardware, we have 120 milliseconds. So a difference of 30 milliseconds even in idle mode. If the host is on load, the result is even higher. We have here encoded in CPU around 200 milliseconds compared to still 120 milliseconds because the hardware encoder doesn't change. And the same with fully loaded CPU, we see an increase to 250 milliseconds. So you can imagine this is an additional latency that is quite bad, especially for applications that use, for example, server-rendered cursors like Autodesk products, AutoCAD. As I would say my favorite application that doesn't really work with H.264, and if you now use NVENC, I'm sure there is a big improvement. But there is even more. As we don't use the CPU for all the encoding, we can get higher host density. Our performance team measured with Esri, and they got a result that we have around 18% better host density if we use NVENC. So, what's the conclusion? Using NVENC, we have latency reduction, which is, I would say, the most important thing. We see an increase in frame rate. It's not that big, but it's there. And we can reach increase in density, which is also quite important, because with the...
So what is the cost of using NVENC? How many cores do you additionally need for encoding a normal session?
In general, we say for Desktop, you should reserve one vCPU only for the encoding stream. So that's...
But okay, let's say that goes to NVENC. How many more cores of NVIDIA, the grid card, do I need for NVENC? Because I'm shifting it from the CPU to the GPU.
No, it's a separate hardware on the grid card that does the encoding. It doesn't leverage the rendering engine nor any other stuff.
It's an ASIC, right?
You're not using
But
CUDA cores for.
you're not using CUDA cores, for example. It might be possible to encode in CUDA, but that's...
Okay, then
that's
you lose the
something
power.
that- Yeah. So that's the last thing. It's the last thing. But for sure, you have to care that you have enough encoding hardware. Maybe I go back.
What happened when you overcommit?
That's a
Great
good
question.
Yes.
So we changed that question. Do we support it on Kepler? Because encoders are on Kepler cards as well, K1s and K2s. No, we don't. Why don't we if we have those encoders on a K1 and a K2? Because there's only like 9 of them, which would really be crappy scalability, and the users that would end up off of that would have a very different experience. You suddenly inject 50 milliseconds into a user's experience from a latency standpoint, that user is going to hate you, right? So the last thing you want is the first couple of users getting it. So from NVIDIA's perspective, even though it works, we don't support it because we can't deliver consistent, great user experience across all the users. So we don't support it on a K1 and a K2.
I'll make it short. On M16, we can get in total 32 VMs, and we have 36, I would say, encoder streams with 30 frames. So this should be really sufficient to do all the encoding with the grid card. Compared to K2, we have 6 streams and a maximum of 16 VMs. So it's quite easy to see that it won't be sufficient for a K2 to have all the encoding in hardware.
What about the M10?
That means that 28 users are hard limit.
It's not a hard limit. It's only the measurement if we believe that each of these users currently uses 30 frames. So on a M10, we don't believe that each user is using 30 frames, and therefore we have for sure more than 28 streams if we have lower frame rates. Okay.
And what will happen when overcommitment comes now? That was the first question.
For
More streams, when I have more streams that you can handle.
right now, we support, well, I take on an M60, you have more streams than you can have vGPU profiles, so it shouldn't happen. Unless you're, if you're using Blast or you're using vGPU, you're never gonna run out, but you can't put more users on than you have profiles available, and we have more encoders than you have profile slices. So it shouldn't happen.
It shouldn't have.
If you can figure out how to break it, don't open a ticket because we're gonna make fun of you. No, the in theory you just can't architect to that level.
Okay.
Yeah.
Okay, so let's have a look on the Citrix part. Currently, Linux VDA 1.2 is supporting NVENC already, but only Red Hat 7.2 is supported with HDX 3D Pro. And it's good to know that as default, SynWire Plus is enabled as codec for Linux. So what you have to do is, at first, switch it over to H.264 to get the H.264 capabilities, and in another step to enable NVENC. I will show this the next slide. One more information, Citrix currently only supports pass-through GPU, at least with sensor 6.5. And it was announced recently with sensor 7 that they will also support vGPU on Linux. It's still tech preview, but it works. I've not tested it on my own, but it definitely works. And they added more OSs like CentOS and SUSE to support.
What is less?
SUSE.
SUSE Linux and the word cell. There you go. It's one.
I did a screenshot on my Linux VDA to show the capabilities of NVENC. For sure it's unreadable at the behind, but I will show what I do. We see here the CTX graphics process. In this screenshot without NVENC, we have 35% CPU load for the encoding. With one and the same use case, it's car visualizer. I did the same after enabling NVENC. This is the key if you want to do it on your own. And now CTX graphics process is down here with 4% of CPU. So there is a difference of 30% CPU load on this single VM. So you can imagine that you now can increase your host density if you're using NVENC. And on Windows, as I said, unfortunately Citrix didn't release NVENC support with the latest 7.9 VDA. It was at least announced internally just before the release, but it didn't happen. So currently no NVENC support at all, but it's definitely planned to introduce in one of the next releases, hopefully 7.10. But I prepared the beta code, and there is one short anecdote about it. NVENC as feature was included in the VDA one time ago. If you use some quite old VDA, for example 7.6 or 76300, there is still the code included, so you only have to switch it on with a registry key and it works. But it was totally removed with 7.7, 7.8. I have a better code for 7.8 and I want to show it, or I try to show. Depending on the wireless, because it's incredible slow here. This is a SolidWorks application. I created a motion here. And the interesting thing is, now NVENC is enabled. We have here the encoder CPU time. It's around 0 to 1, maybe 2% of CPU load. I'm simply changing the encoder type. And now I disabled NVENC. Unfortunately, the line is too slow, so you cannot really see how the CPU is increasing. In general, you should have 4 megabit for this use case. So you would have around 35 to 45 frames, and the CPU load without NVENC is then around 10 to 15%. Even with such an, I would say, low to medium use case. Now as the frame rate is such low, there is not that big difference. But I think you, in general, can imagine that it definitely makes a difference.
Okay, the bandwidth is bottleneck now, not the CPU. The bandwidth is
The
not...
bandwidth here, yes, sure. You see here, the bandwidth it's less than 1 megabit, and that's not sufficient in any case for HDX 3D Pro. Sometimes even lower. Okay, but I think you see at least the difference here in CPU load, and that's what will come with the next Xendesktop release.
If you have Xendesktop 7.6, you could use it.
You could use it in theory, for sure. It's not supported at all, but some of the guys they tested it in the past and it worked. And I tested it also in the past. Yes, it worked. Maybe there are still some issues. Maybe that's the reason why Citrix doesn't officially support it yet, and they removed it. Maybe especially in the case that someone knows the key and enables the key, and that's it.
Cool. Excellent. Thank you very much.